Hi children, welcome to another chemistry session. Today our revision class is on second chapter, unit 2, structure of atom. First year topic, unit 2, structure of atom. We are going to have a review through the NCERT, important points and a few topics just peripherally outside the NCERT also, which is very important for the competitive purpose that we are going to review. Okay. So, structure of atom, the fundamental topic which actually coming in the lower classes itself regarding the structure of atom, fundamental particles, subatomic particles you are learning in the lower classes itself, right? Electrons, protons, neutrons, various subatomic particles. The most important three subatomic particles we are concentrating is on proton, neutron and electron. They are categorized as nuclear system and extranuclear part. In the nuclear system, we have protons and neutrons. Collectively, we call it as nucleons. And the extranuclear part contain electronic system. That is what we are going to concentrate upon with the various old theories and modern quantum mechanical model of atom in this session. A quick, rapid revision through the topic. Even though there are three fundamental particles we are talking about, there are many fundamental particles. There are many fundamental particles, almost more than 30 different kind of fundamental particles are said to exist, about which we are not supposed to go through in detail in this session. Basically, there is proton, neutron, electron, positrons, negatrons, pions, positive pions, negative pions, neutral pions, gluons, quarks, many terms you might have heard about, right? Those who are interested can go deep into those areas and have a review on those kind of fundamental particles and their nature and how they are influencing in the overall explanation of structure of atom. Okay, we will go through the NCERT content basically, which is most important from the competitive point of view. To start with, as we know, the Dalton's atomic theory, which we have gone through in the chapter 1, Dalton's atomic theory, from there it starts. Everybody know the term atom was coined by atomos. Atomos means indivisible. Atoms cannot be divided further. Atoms are not subdivided further. That was the terminology coined atomos, from where atom came. But we know atoms are divisible and there are subatomic particles, right? The first talk on the subatomic particle happens with electrons. That is the discovery of electron, actually forwarded by Michael Faraday. But we know the discovery of electron, the credit goes to Thomson. And William Crookes, who conducted the Crookes experiment in cathode ray tube for explaining the characters of cathode rays, which is basically in the initial stages were J.J. Thomson and his students called negatrons. Negatrons, that was the name initially given. Later on, it was explained as electrons. Basically, it is cathode ray. It is the William Crookes discharge tube experiment explained about the characteristics of cathode rays. Hope you remember the diagram and the experiment concept. This is cathode ray tube experiment. Cathode ray tube experiment. So I will take a copy to here. This is CRT experiment. All of you remember, and even in the lower classes you are learning about this, I believe. You see that a cathode ray discharge tube is like this. There is a cathode, two terminals, cathode and anode, and is connected. Tube is connected to a vacuum pump. Why vacuum pump? We need to maintain a low pressure inside the system, because at high pressure the air is a bad conductor of electricity. We are filling some gases inside, and that's a bad conductor of electricity at high pressure. When you maintain a low pressure, it is easy to ionize, and thereby we are able to get the cathode ray discharge. A high voltage is applied over the terminals. A high voltage is applied and we maintain a low pressure gas inside the steam and inside the system, and we can see a stream of particles originating from cathode will migrate towards anode. A stream of particles originating from cathode will be migrating towards anode like this, which is termed as cathode rays. And we can see the anode is taken perforated anode through which the cathode rays will migrate and falling on a fluorescent coating given. And that fluorescent coating is giving us the existence of such rays, and the characteristics of rays were studied based on this experiment, CRT experiment, cathode ray tube experiment, conducted by William Crookes, right? These all experiments and facts, it is known to all, and just reviewing, that's all. And there is a topic on characteristics of cathode rays. Hope you remember the cathode rays starting from cathode to and move to anode. They themselves are not visible, but we are getting the existence of that cathode rays when they are striking on a screen where a coating is given, phosphorescence coating is given, fluorescent coating is given, right? They are electrical, the absence of electrical and magnetic field, these rays travel in straight lines. These facts everybody know. In presence of electric and magnetic field, they behave like negatively charged particles. Cathode rays are negatively charged particles. Moreover, the characteristics of cathode rays, that's a very, very important point. Characteristics of cathode rays does not depend on the material of the electrode and the nature of the gas present in cathode ray tube. Most important point. The characteristics of cathode rays is irrespective of the material of electrode used. Number one, the gas filled inside the system. That means it is a universal matter content. If you take hydrogen gas, if you take helium gas, if you take any type of metal electrode, the cathode ray characteristics remain the same. That means it is a universal matter content. We can conclude that electrons are basic constituent of all atoms and it is universally same. Right? That is about cathode rays. And a very important experiment, charge to mass ratio calculation. Charge to mass ratio calculation done by J.J. Thomson. And experiment, I hope you remember the diagram. Within a cathode ray tube, a cathode ray is generated producing a high voltage and is allowed to fall on a screen. And there is a magnetic field and electric field is provided. In the absence of electric field and magnetic field, they will travel straight line and fall at point B. While if you introduce magnetic field or electric field, they will make a deviation in such a way that their characteristics is negatively charged. So if you give electric field, they will deviate. If you give magnetic field, they will deviate. And the deviation depends on the charge that you are giving. Now, the magnetic field, what he did? The magnetic field and electric field, he adjusted in such a way, controlled manner, that the two fields are adjusted in a controlled manner that it travels in the straight line. And looking at the potentials applied, the charge that been applied, he was able to calculate. We don't have to go in deep into the derivations or concepts related to that. By controlled analysis of the movement, controlling the movement of cathode rays, he was able to establish a very important characteristics of cathode rays, that is E by M value. Very important. Our point is, competitively, our point is to know that value. E by M value of E by M ratio of electrons, cathode rays. This is the E by M value of cathode rays, all of you know. What is the value? E by M value for cathode rays. You have to memorize the data, 1.7588 into 10 raised to 11 coulomb per kilogram. 1.7588 something, 10 raised to 11 coulomb per kilogram. Charge to mass ratio. You can expect some comparative questions of charge to mass ratio of various fundamental particles and some other particles, etc. And there is one more experimental talk is happening. There is one more experimental talk happening regarding the charge of electron. Millikan's oil drop experiment. Once again, we don't have to go deep into the experimental context. Millikan's oil drop experiment. You see, this is the Millikan's oil drop experiment, and the experiment is very, very important, but we don't have to go deep into the content. This is the diagram explaining Millikan's oil drop experiment. He was able to make some, using some atomizer, the oil droplets are fed into the chamber. And there are two plates you can find. On the top plate there is a small hole, and through small hole the oil droplet is allowed to fall down. And he was studying the falling speed of that oil drop, how the oil drop is falling freely. You know, an oil drop when falls, there are 2-3 different forces operating. What is the forces operating? One is gravitational force with which it is falling down. Then there is a viscous drag. When an oil is dropping, there is a viscous drag. You might have seen the drop is falling like that. It's not exactly spherical. There is a viscous drag. So there are different forces that is operating the falling of an oil drop. So he studied how oil drop is falling freely. Then, you know what he did? He using the X-ray source, he ionized the gases over here. And when the gas is ionizing, electrons are ejected, and that electrons are adhering to the surface of the oil drop. And now it is a charged oil drop. How the charged oil drop is falling down? He was able to study by giving potential to the plates. This is charged plates. Using that charged plates, he was able to control the movement of the falling velocity of that oil droplet, and thereby he was able to calculate what is the unit charge added on the surface of the oil drop. That is Millikan's oil drop experiment. I'm just revealing the ideas concerned just for the information purpose. We are not expecting any competitive questions from that. And with which he was able to identify a unit charge. What is a unit charge? He got the data. Unit charge as 1.6. You see that? E is equal to 1.6 into 10 power minus 19 coulombs. Everybody know what is the charge of one electron. What is the charge of one proton? What is the unit charge? 1.6 into 10 power minus 19 coulombs. Now E by M ratio we have. E value we got. Now you can find out the mass of electron. Mass of electron will be E by M. That will give you the rust mass of electron. And this is the rust mass of electron. 9.1 into 10 power minus 31 kilogram. So all these data and the concerned experimental facts, which you can just roughly go through, but the data very important. Okay. So that is the initial portions that are coming. Then there is the talk on discovery of protons. Discovery of protons, canal rays. By experimenting cathode rays, at the same time we can see that some adjustments done on the cathode ray experiment by taking perforated electrodes. It was observed that an oppositely charged stream of particles are migrating in the opposite direction to the cathode rays, and later on it was discovered as protons. If you take hydrogen atom, it is basically called canal rays. If you take hydrogen atom, it is protons, H+, right? And that was the discovery of protons. They migrate in the opposite direction. And the characteristics of cathode rays, very, very important. Unlike anode rays, unlike cathode rays, mass of positively charged particles depends upon a very, very important point. There we said, cathode rays are independent of electrode used and gas used, while anode rays, protons are depending on the gas that you use in the CRT tube. If you take hydrogen, you get H+. If you take helium, you get a different cation, right? It is simply ionized atoms. Cathode rays. Right? So cathode rays will be depending on the gaseous sample that you use in the experiment. The other properties are quite similar. They are charged particles. Cathode rays are negatively charged. Anode rays are positively charged. They migrate in the electric field and magnetic field in such a way that exhibiting positive character. Right? So that is about the cathode ray, and you must go through the relevant points concerned regarding cathode rays. Then there is a talk on discovery of neutrons. Neutrons discovered by Chadwick after a long time. So electrons, proton, neutrons and their discovery. Then various atom models. Various atom models. You see, this table is very important regarding the characteristics of the three fundamental particles: electron, proton, neutron. Their absolute charge, their relative charge, their mass, and their mass in unified mass value. And you can see neutrons will be slightly upper hand on mass compared to proton. Every point concerned like this is very, very important. And this table is also very important. Then the topics learned in lower classes itself. Thomson atomic model, Thomson plum pudding model of atom. Atom considered as a positive sphere and electrons are embedded like that. All of you know Thomson model of atom. And while you learn Thomson model of atom and the side by, there are some informations given regarding how alpha particles, beta particles, gamma radiations, what is an alpha particle, how the radioactivity was discovered, and what are the radioactive disintegrations and emitting particles, importance of alpha particle, beta particle, gamma rays, and their migration ability, etc. are commented in this column, which you must go through. And this is one of the most important experiment. I don't have to tell you. The experiment which is written in golden letters in the history of science. Rutherford alpha scattering experiment. See, the basic nature of atoms and their overall periphery was clearly explained by Rutherford atom model. What was the experiment? Alpha scattering experiment, gold foil experiment. There was an alpha particle source was ejected and is allowed to struck on a thin film of gold, very thin film of gold. What was the observation? Almost all particles seems to be passing through the gold foil undeflected without any disturbance. Majority of alpha particles were passing through the gold foil without any disturbance. A very few found to make a deflection. And a very few, 1 out of 20,000. 1 out of 20,000 found to bounce back. And that given a clear picture regarding the nature of atom and its mass concentrated basically about the nucleus. And he was able to conclude with this experiment. Alpha particle means positively charged particles. Positively charged particles freely moving through the atom, gold foil. Gold foil means atoms of gold. He was able to make a conclusion. Majority space of atom is empty. Major space of atom is empty. And the entire mass of atom is concentrated on a very small point, which he is trying to compare. If the overall size of the atom is compared to a big stadium, a small ball kept at the center of the stadium is equivalent to nucleus. The entire mass is concentrated on the nucleus and is a highly dense region and contain positive charge. And you are passing alpha particle. Alpha particles are positive particles and the nucleus is positively centered. And majority of alpha particle passing through because no issue. And a minority when comes close to the nucleus getting deflected. A very minority which is coming straight to the nucleus will bounce back. 1 out of 20,000. That was the main conclusion that is evolved from the experiment, alpha scattering experiment. And regarding the size of atom, size of the nucleus. Size of atom, size of the nucleus. Size of atom, if it is compared to be 10 raised to minus 10 meter range, size of nucleus is 10 raised to minus 15 range. That means 10 raised to 5 difference. 10 raised to 5 difference between the size of atom and size of the nucleus. That was the conclusion made by alpha scattering experiment, which is still valid. A very important experiment written in golden letters in the history of science, right? And you can very well find the comparison. Whatever that I told. Here, see here, the radius of the atom is about 10 raised to minus 10 meter. Radius of the nucleus is 10 raised to minus 15 meter. 10 raised to 5 meter difference between the radius of atom, overall radius, and the radius of nucleus. Such conclusion, important conclusion, was able to made by Rutherford experiment. And you know, Rutherford actually was able to explain the existence of protons, right? Then there is a talk on atomic number, mass number, etc. Atomic number, everybody know what is atomic number? Atomic number means number of protons. For a neutral atom, number of protons is equal to number of electrons. What is mass number? Mass number is number of proton plus neutrons. Number of proton plus neutrons is mass number. So atomic number means number of protons, which is equal to number of electron for a neutral atom. For a charged species, it will be different. And mass number is equal to proton plus neutrons. And related to these things, you must know what is meant by isotopes, what is meant by isobars, what is meant by isotons, etc. Isotope means same mass number, isotope means same element, different mass number. Same element, different mass number. For example, if you take carbon, there is, let me reduce the size. Carbon 612, carbon 613. You see, the mass number is different. That is called isotope. Same element, different mass number. Why the difference in mass number? All of you know. Due to difference in number of neutrons. So isotopes arises due to difference in number of neutrons. Here, number of proton is 6. Number of electron is 6. Number of neutrons will be 12 minus 6. That is number of neutrons. There are 6 proton, 6 electron, 6 neutron. What about here? There are 6 proton, there are 6 electron, and 13 minus 6, 7 neutrons. So difference between the neutrons lead to isotopes. So isotopes, same element with the same atomic number, different mass number. Isobar, what is isobar? Different elements, different atomic number, same mass number, called isobars. So same atomic number, different mass number, isotope. Different atomic number, same mass number, isobar. Isoton, what is isoton? Same number of neutrons, called isotons. Isodiaphers, not in the NCERT, but I am just telling you. Isodiaphers having same isotopic number. What is isotopic number? Isotopic number, important in nuclear chemistry and all. Isotopic number means the difference between neutron and proton is called isotopic number. Okay, the elements having same isotopic number called isodiaphers. So isotopes, isobars, isotopes, same element, same atomic number, different mass number. Isobar, different atomic number, same mass number. Isoton, same number of neutrons. Isodiaphers, same isotopic number. What is isotopic number? The difference between neutron proton is called isotopic number. All these things you need to go through regarding the characteristics of explaining an element, and various isotopes and their relative abundance, etc. are accumulated here. Drawbacks of Rutherford model, everybody know. What was the drawback of Rutherford model? Rutherford said, see, whatever he said regarding nucleus is still valid. But what he said regarding electrons, he said electrons are revolving around the nucleus in a definite path constantly, which is not possible. Across see, it was like nuclear model of atom. How around the sun the planets are revolving, electrons are revolving around the nucleus. Okay, around the sun planets can revolve, no problem. Infinitely it can revolve, no problem. But around the nucleus, electrons cannot revolve like that. Because nucleus is a charged system, electron is a charged system. According to electrodynamics, when a charged particle moving around another charged particle, it will lose energy. Once it loses energy, it will change the path. And the path moving like this, the electrons moving like this, it will change the path. And ultimately, it will follow a spiral path, and it is collapsing with the nucleus. It is not explaining the stable nature of matter. It is not explaining the stable nature of an atom. That was the main drawback of Rutherford model. You might have heard about, you might have learned. Then development leading to Bohr model of atom, dual nature of electromagnetic radiation, experimental results regarding atomic spectra. We are going to talk about electromagnetic radiation. This is electromagnetic radiation. All of you know. Electromagnetic radiation means the radiation constituting electrical waves and magnetic waves. What is the importance of electrical and magnetic waves and electromagnetic radiation? Suppose the movement of electric wave is like this. The movement of magnetic waves will be mutually perpendicular like this. So if it is in one, if one vibrations are through y-axis, y plane, the other will be in the x plane, mutually perpendicular. So electric and magnetic fields are mutually perpendicular. And see, if this is electric field, this is magnetic field, and this is the propagating direction. They are mutually perpendicular and also perpendicular to the propagation of the radiation. This is the propagation direction. This is the propagation direction. This is electric field in the vertical plane, and this is magnetic field in the horizontal plane. They are mutually opposite. Also opposite, mutually perpendicular. Mutually perpendicular, also perpendicular to the propagation direction. That is electromagnetic waves. And what are the electromagnetic waves? Everybody know. These are the electromagnetic waves, and this is called electromagnetic spectrum. This we call it as electromagnetic spectrum. And studying about electromagnetic spectrum is very important. Studying about electromagnetic spectrum is very, very important. Electromagnetic spectrum means arrangement of various radiations in the increasing order of frequency, in the decreasing order of wavelength. Right? You can see the arrangement of various radiations. It is arranged in the decreasing order of frequency from left to right, while increasing order of wavelength from left to right. Gamma rays, maximum frequency. Gamma rays. Gamma cosmic rays, X-rays, UV, and a very small region in the 400 to 700 nanometer wavelength, we have visible region. What we can view is very small region. Then lower energy radiations, infrared, microwave, radio waves, long radio waves, it comes like that. Please understand, from left to right, decreasing frequency order and increasing wavelength order. Okay, and this is the small region which is visible to us, which we call it as visible spectrum. This is visible spectrum, and the overall is called the electromagnetic spectrum. Concerned to electromagnetic spectrum and electromagnetic waves, you must learn about frequency, wavelength, wave number, so many things. Frequency, wavelength, wave number, crust, trough, amplitude. So many things which you are learning in physics regarding waves. How their relations between them are. Nu is equal to c, velocity of light. Nu is equal to c by lambda. You can expect problems based on frequency, wavelength, velocity, wave number. Wave number, you know, nu bar is equal to 1 by lambda. All such relations you must go through and review. Regarding frequency, regarding lambda, regarding wave number, the relation nu is equal to c by lambda, the relation nu bar is equal to 1 by lambda, amplitude, crust, trough, so many things related to waves, and they are simple problems. A few problems are given in the NCERT itself, and that was previous questions also. Please review and go through to solving all those things. Okay. That's about electromagnetic spectrum. I was talking about a few problems like this. You see, few problems like this which you can find in the NCERT, simple problems related to wave parameters. What are the wave parameters? Frequency, wavelength, wave number, velocity, etc., etc. Then there is a talk on Planck's quantum theory. You know Planck's quantum theory. Planck's quantum theory is related to, it is a idea which came. We had a classical theory. Many topics, many observations were unable to be explained effectively by classical theory, Maxwell's classical theory. And then came quantum theory. What are the properties? Black body radiation, it was unable to be explained by classical theory. Photoelectric effect, it was unable to be explained by classical theory. All these phenomena were explained by quantum theory. Right? What are the phenomena? Black body radiation, hot body radiation, photoelectric effect. This we are going to discuss in detail. Variation of heat capacity of solids as a function of temperature. Heat capacity versus temperature. Then line spectra, atomic spectra was unable to be explained by classical theory. So classical theory and quantum theory, that's a very important topic in the chapter. All of you know, classical theory says that according to classical theory, the transmission of energy is happening, the radiations are transmitted in a continuous manner. The energy transmission is continuous in nature. That is classical theory. I am talking about the fundamental basic difference between classical theory and quantum theory. What about quantum theory? What is quantum theory talking about? Quantum theory proposed by Max Planck. He said energy transmission is not continuous but discontinuous in the form of small packets of energy. It's not like this. It is like this. It is in the form of discontinuous manner. Small packets of energy. And each packet is called a quanta. Each packet is called a quanta. In case of light, it is called a photon. And he said energy of quanta is directly proportional to frequency of radiation. And energy is equal to a constant h into nu. H is called a Planck's constant. All of you know 6.626 into 10 power minus 34 joules second. You know that. Planck's constant. Right? E is equal to h nu. And this is called one photon, one quanta, one packet of energy. Energy of radiation depends on the frequency of the radiation. And E is equal to h nu. H, what is h nu? One packet of energy. Right? One more thing he is commenting. It is happening, the energy transmission is happening in the integral multiples of quanta. E is equal to n h nu. What is n? N is equal to 1, 2, 3, 4, etc. It can be 1 packet, 2 packet, 3 packet, 4 packet, 5 packet. It can't be 2.5 packet. It can't be 3.25 packet. Fractional is not possible. Energy transmission happens in the integral multiples of quanta. This is the fundamental difference between quantum theory and classical theory. Classical theory suggests that energy transmission is continuous in nature, while quantum theory suggests that energy transmission is not continuous but discontinuous in the form of small packets of energy. And this could explain various phenomena like black body radiation, hot body radiation, photoelectric effect. That is what we are going to discuss further. This is black body radiation. This is black body radiation. You might have maybe there in your memory. What is hot body radiation, black body radiation? Every hot body, every body when heated, it will start emitting radiation. And the emitted radiation depends on the frequency of the emitted radiation depends on temperature. So according to the energy of the system, according to the temperature of the system, the radiations are emitted from hot body. And it's called a hot body radiation, black body radiation. There is a definition given. What is a perfect black body? Black body means which can absorb all type of radiation, which can hence emit all type of radiation. That is called a perfect black body. A perfect black body is demonstrated in the diagram. A light entering into, this is a spherical system where inside some graphite or carbon black coating is given, and through a small hole, a light is entering into the system, will never come back. It will undergo total internal reflection and it will be settled inside. This is a demonstration of perfect ideal black body. A black body means which can absorb all radiation. And black body radiation experiment is done, and some observations are given here. Hope you remember that explanation. When an iron rod is heated in a furnace, you see what is happening. An iron rod when heated in a furnace, first it turned dull red. Progressively it becomes more and more red hot. As the temperature increases, as is heated further, emitted, it becomes white and then becomes blue at a very high temperature. At a very high temperature, it becomes blue. You know what is the importance of blue? Blue is high energy visible radiation. At a high temperature, you are getting blue means as the temperature increases, the energy of the system increases, the emitted energy is also increasing. So the emitted energy and its frequency is coming as a function of temperature. This is not explained by any classical theory, right? You need to go through this graphical diagram, which is explaining the wavelength versus intensity of light emitted. Wavelength versus intensity of light emitted. You can see at a particular temperature T1, what is observation? This is an experimental observation. And you see that as the wavelength increases, the intensity is also increasing. As the wavelength increases, the intensity increases and comes to a maximum point. And then the intensity decreases with the further increase of wavelength. This is the observation happened. So at a particular temperature, you can have a particular maxima. And that maxima wavelength is the experimental observation. At this temperature T1, this wavelength we observe. You see, as the temperature increases, I am taking a new high temperature, the wavelength decreases. Wavelength decreases means frequency increases. Hope you understand. Frequency increases means energy increases. You know, E is equal to h nu. That is equal to hc by lambda. As the temperature increases, it's a measure of energy. Energy increases. When the energy increases, frequency increases. When the frequency increases, lambda decreases. At a temperature T1, you have lambda 1. At a temperature T2 higher than T1, you have lambda 2. Lambda 2 is less than lambda 1. Suppose I am taking a temperature T3. What is the graph? What is the graph? It will be T3. The graph will be like this. You see, the maxima lambda will be again to left. So as the temperature increases, the graph is coming more and more to left hand side and the peak increases. The intensity peak increases. This is hot body radiation experiment, experimental graph, which is explained on the basis of quantum theory. And that's about hot body radiation. Now, there is an important topic, all of you know, photoelectric effect. Photoelectric effect. Photoelectric effect observed by Heinrich Hertz and detail explained by Einstein. Photoelectric effect. I don't have to tell you. This diagram is very, very familiar to all. Experimental diagram for the photoelectric effect. Very familiar to all. You see, when radiation of suitable frequency falls on a metal surface, electrons are ejected. That is photoelectric effect. It is the phenomenon of ejection of electron. When radiation of suitable frequency falls on it. The minimum frequency required, all of you know, it is called the threshold frequency. So when a minimum frequency called the threshold frequency falls on the surface of a metal, electrons are ejected and the phenomenon is called a photoelectric effect. And the minimum frequency required, it depends on the nature of the metal. And which metal has in the periodic table, which metal has got very high tendency to show photoelectric effect? Means a very low energy required for causing photoelectric effect. I think many of you know. Yeah, it is alkali metals. In alkali metals, who? In alkali metals, who? Cesium. Cesium, the most electropositive element in the periodic table, the one which has got a very low ionization enthalpy, need minimum energy, minimum frequency to cause photoelectric effect. That's why cesium is used in photocells. While if you go to other elements, the threshold frequency required will be high, increasing. Okay, what is threshold frequency? Minimum frequency required to cause photoelectric effect. What is photoelectric effect? Ejection of electron from the metal surface when radiation of suitable frequency falls on it. Right? And if you are giving a higher energy, that will be transmitted as kinetic energy to the ejected electron. I think all of you know kinetic energy of ejected electron, half mv square is equal to h nu minus h nu 0. H nu minus h nu 0. This is threshold frequency and this is called the threshold energy. Nu 0 is threshold frequency. H nu 0 is called threshold frequency. It is also called work function. It is represented as psi, work function, the minimum energy to cause photoelectric effect. Suppose minimum energy is 4 unit, and imagine the energy that I am giving is 10 units. Will there be photoelectric effect? Yes, there will be photoelectric effect. And what happens? 10 energy I am giving, the required energy is 4 unit, 10 minus 4, that is 6 unit energy will be transmitted as kinetic energy to the ejected electrons. So the kinetic energy of ejected electron, a very important study done by Einstein. The kinetic energy of ejected electron is equal to the difference between energy that you supply, h nu, and h nu 0, that is work function of the metal, that will be transferred as kinetic energy to the ejected electron. Law of conservation of energy. Suppose work function is 4 unit and imagine I am supplying only 2 unit. Will there be photoelectric effect? No, because minimum energy required is 4 unit and what I am giving is only 2 unit and there won't be any photoelectric effect. I am passing a radiation having energy 2 unit. The minimum energy required is 4 unit. There won't be photoelectric effect. It should be on or above 4 unit. What if I am supplying an energy radiation equal to 4 unit and the metal having work function 4 unit? Suppose I am giving a radiation 4 unit. There will be photoelectric effect and ejected electron will have 0 kinetic energy. 0 kinetic energy. Right? So these are the important area concerned to photoelectric effect and important equation concerned to photoelectric effect. Kinetic energy of ejected electron half mv square is equal to h nu minus h nu 0. You can expect many problems concerned to this. And you can very well see a few metals having their work function quoted. What is work function? Work function means threshold energy, minimum energy required to cause photoelectric effect. You see lithium, sodium, potassium, magnesium, copper, silver having their work function. You see lithium, sodium, potassium, lithium, sodium, potassium. You see the value, potassium minimum, because alkali metals as you come down, their size increases, they can easily lose electron. So the value is decreasing. While if you go to copper, silver, the value is pretty high. Hope you understand. Imagine, and let me ask you one question. Imagine, over these metal I am taking for experiment and I am passing a radiation having energy equal to 3 electron volt. I am supplying a radiation having energy equal to 3 electron volt over all these metal taken for experiment. Which all metals will cause photoelectric effect? Will lithium? Yes, lithium will show because minimum required is 2.42. I am giving 3. Will sodium? Yes, minimum required is 2.3. I am giving 3. Will potassium? Yes, minimum required is 2.25. I am giving 3. What about magnesium? No, because minimum required is 3.7. I am giving only 3. So the energy given by the radiation is only less than what is actually required. What about copper? No. What about silver? No, because minimum required is 4.3. We are supplying a radiation energy equal to 3. So if we are supplying a radiation 3 electron volt, lithium can show photoelectric effect, sodium can show photoelectric effect, potassium can show photoelectric effect, magnesium cannot, copper cannot, silver cannot. And these kind of conceptual questions and many numerical questions you can expect from the area. Please, we need to practice. We are going to practice in detail in the classes. That is about the importance of photoelectric effect. Then our talk is on dual behavior of electromagnetic radiation. Dual behavior of electromagnetic radiation, particularly atomic spectra. We are going to discuss about spectrum. Spectrum, atomic spectra. What is meant by atomic spectra? Atomic spectra we can easily understand from this diagram. Hope you remember this diagram. This is atomic spectra explanation, absorption and emission spectra. Absorption and emission spectra. You see, we will discuss this one first and then that. This is absorption spectra. This is second one, second diagram. I am taking a white light source. You know, white light contains 7 colors. VIBGYOR. That white light source passing through a gaseous sample. This is a gaseous sample, say for example, hydrogen or any gas. Now what happens is that sample of gas, the matter inside here will absorb certain radiation from white light and the remaining radiation comes out. And when taken for a picture passing through a prism, when taken for a photographic film, and when you take a photo, you can see this is what the diagram you get. Out of many VIBGYOR radiation, many radiations are missing. You see the blue color is entirely missing. And many lines you can find dark lines. It is missing. Where it gone? It is absorbed by this sample of matter. And the spectrum obtained is called the absorption spectrum. From white light, all radiations which are equal to excite the electrons here are being absorbed. The atom getting absorbed, absorbing radiation, it get excited. So various energy radiation from white light absorbed by the sample of matter, and when the remaining radiation come out, and when you take a photographic film print out, you find many radiations are missing. And now this sample of matter gets excited. Now that excited sample is emitting the radiation. Whichever it absorbed previously is emitted. Now that emitted radiation passing through a prism, when you take a printout, you can see this is what you get. That means entire region missing here will be reproduced here. You see the bluish region is missing. The bluish region is missing. That region is coming here. So whatever is absorbed here is emitted here. So the previous one is called absorption spectrum. This is called emission spectrum. And you can find there are fine lines which are absorbed here is also getting reproduced here. This is absorption spectrum. This is emission spectrum. Hope you understood. So a white light containing 7 colors passed through a sample of gas. So many radiations absorbed by the gas and it gets excited. So the remaining radiation, when you take a printout, you can see so many radiations are missing. Actually, it is available here and the gaseous matter got excited. Now that excited sample, when it emits radiation and when you take the printout, when passing through the prism, when you take a printout, you can see whatever is missing here is emitted here. So these two diagrams are complementary to each other. Absorption spectrum, emission spectrum are complementary to each other. Hope you get the picture. Clear? That is regarding the absorption spectra, emission spectra, and leading to atomic spectra. Atomic spectra, I think all of you heard about. Atomic spectra is unique in character. Atomic spectra may be considered as fingerprint of atoms. They are showing the individual characteristics of atoms. That is how we distinguish between elements. Elements are distinguished by atomic spectra. And that study is called spectroscopy. New elements when discovered, they are identified based on a database already we have. Compared with this, we check for a new element's existence based on their spectroscopic analysis. And this kind of observation done by different elements, we call it as spectroscopy, atomic spectra. Our special reference is atomic spectra for hydrogen atom. Our special reference is for atomic spectra for hydrogen atom. When we experience atomic spectra in hydrogen atom, this diagram is very important. Hydrogen atom is giving different atomic spectra in different region, mainly 3-4 important series of spectral lines. What are the important series of spectral lines shown by hydrogen? Hope you remember. This is a diagram, important diagram from the NCERT showing the atomic spectra, various hydrogen spectra series, Lyman series, Balmer series, Paschen series, bracket series, P-fund series. An excited electron jumping to n equal to 1, that is Lyman series, high energy series. The range of radiation comes in ultraviolet region. While excited electron jumping to n equal to 2, that is second orbit, that is called a Balmer series. Right? Then Paschen series, bracket series, P-fund series. Hope you see this table. The name of the series N1, N2. N1, N2. N2 is the excited state, N1 is the de-exciting state. So an excited electron coming from 2 to 1, 3 to 1, 4 to 1, that is ultraviolet region, Lyman series. An excited electron jumping from 3 to 2, 4 to 2, 5 to 2, that is Balmer series. 4 to 3, 5 to 3, 6 to 3, that is Paschen series. 5 to 4, 6 to 4, 7 to 4, bracket series. 6 to 5, 7 to 5, 8 to 5, P-fund series. There is Humphrey series, you might have heard about sometimes. Humphrey series. Humphrey series, N1 equal to 6, N2 equal to 7, 8, 9, etc. That is also coming under far infrared region. Far infrared region. So there is a series of spectral lines given by hydrogen atom. Lyman series, Balmer series, Paschen series, bracket series, P-fund series, Humphrey series. Accordingly, respectively, the excited electron jumping back to n equal to 1 Lyman series, n equal to 2 Balmer series, n equal to 3 Paschen series, n equal to 4 bracket, n equal to 5 P-fund series, n equal to 6 Humphrey series, like that. These are all various atomic spectra for hydrogen atom, spectral series given by hydrogen atom demonstrated in this diagram. This is called the first line of Lyman series. This is called the first line of Lyman series. And this is second line of Lyman series. This is third line of Lyman series. This is fourth line, fifth line, and this is called the limiting line. An electron coming from infinity to 1, that is limiting line of Lyman series. This is first line of Balmer series, red in color. Second line of Balmer series, green in color. Third line of Balmer series, blue in color. Fourth line of Balmer series, violet in color. This is fifth line, What about fifth line? Fourth line is violet in color. Fifth line, sixth line, seventh line, eighth line, all in violet region. Limiting line. Limiting line means from infinity to 2. That is limiting line of Balmer series. Violet. Because Balmer series, which one first observed, first discovered, it comes in visible region. Visible region range, red to violet. Vibgyor. So fourth line is violet, fifth line is violet, sixth line is violet, seventh line is violet. Right? While others in the infrared, far infrared region. A very important equation everybody should know is regarding the spectral series is nu bar equal to RH into 1 by N1 square minus 1 by N2 square into Z square. We are talking about Bohr atom. We are talking about Bohr atom. Bohr atom means uni-electronic system. Bohr atom means uni-electronic system. Hydrogen, helium plus, Li2 plus, Be3 plus. These are uni-electronic system. We call it as Bohr atom. Bohr atom. For Bohr atom, nu bar is equal to RH into 1 by N1 square minus 1 by N2 square into Z square. Z is atomic number. RH is called Rydberg constant. All of you know Rydberg constant. 109677 centimeter inverse. Rydberg constant. This is regarding atomic spectra of Bohr atom. Atomic spectra of hydrogen. And this formula is very important. And this formula you can use for finding wave number, nu bar, wave number. And you know wave number nu bar is equal to 1 by lambda. 1 by lambda. Right? You can calculate energy. E is equal to H nu is equal to Hc by lambda. That is Hc nu bar. So multiplying this into Hc, you get energy. Multiplying this data into Hc, you get energy. Hope you know that. Okay. You can find the frequency. You can use this equation for finding wavelength, nu bar, frequency, energy of any transition from N2 to N1. N2 to N1 transition, you can use this formula which is called a Rydberg formula. Basically introduced as Balmer formula because Balmer series was observed first. And there are a lot of important formulae which you need to memorize and apply in various numericals which we are going to do in the classes. Bohr model formulas. Various formulae connected to Bohr model. Equation number 1, energy equation. En is equal to E14 hydrogen into Z square by N square. Energy of nth orbit. Energy of nth orbit. Energy of nth orbit of Bohr atom. Which is Bohr atom? Which is Bohr atom? Hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, uni-electronic system. One electron system. You can apply the formula. En, energy of nth orbit is equal to energy of first orbit of hydrogen. What is the energy of first orbit of hydrogen? 13.6 electron volt minus 2.18 into 10 power minus 18 joules. Right? You know that constants. So E14 hydrogen minus 13.6 electron Z atomic number of the species, and N orbit number. Energy of nth orbit. Energy of nth orbit. Okay. Then radius of nth orbit. All these formulae there in the text. I am not commenting anything outside the text now in this content. You can find all these in the text. You see that? En is equal to E1 is equal to this value. En figure. Where is that formula? There in the text only. Yeah, this one. You see that? En is equal to minus 2.18 into 10 power minus 18 Z square by N square joules. Right? I have written in electron volt also. So En is equal to this much electron volt into Z square by N square, or this much joules into Z square by N square. Similarly, radius equation, Rn is equal to A0 N square by Z. What is A0? A0 means radius of first orbit of hydrogen atom, all of you know, 52.9 picometer or 0.529 Armstrong unit. Prof, you know that. Radius of first orbit of hydrogen, which is a constant, into N square by Z. N is the orbital number, Z is the atomic number of concerned species. Suppose you are talking about R34 helium plus, it will be 52.9 into N square, 3 square divided by atomic number of helium, 2. This will give you the answer, like that. So, energy of nth orbit, radius of nth orbit, angular momentum equation, very important formula, angular momentum equation, MVR is equal to NH by 2 pi, MVR equal to NH by 2 pi, another important formula. Angular momentum MVR is equal to NH by 2 pi, N equal to 1, 2, 3, 4, etc. So, H by 2 pi, N equal to 1. 2h by 2 pi, h by pi, n equal to 2. 3h by 2 pi, n equal to 3. 4h by 2 pi, that is 2h by pi, n equal to 4, like that. So it is always quantized. Bohr model is the based on quantum mechanics, based on quantum theory. Bohr model is based on quantum theory. So it is talking about the quantization. So energy of orbit, energy of Bohr orbit, radius of Bohr orbit, angular momentum equation. Try to go through all such formulae. Velocity of nth orbit electron, Vn is equal to 2.18 into 10 raised to 6 meter per second into Z by N. Velocity of nth orbit. So energy equation, radius equation, velocity equation, there are whole lot of numericals we are going to encounter and different relationships and objective questions based on this. Bohr model, all formulae, very important. That's all coming from this area. Then towards quantum mechanical model, dual nature of matter. Towards quantum mechanical model, dual nature of matter, de Broglie's relation, dual nature of matter, de Broglie relation. De Broglie relation, explaining dual nature of matter, right? Hope you remember what you studied. E equal to mc square, particle nature of matter, E equal to h nu, quantum theory. Right, equating the two, we get mc square equal to h nu, that is mc square is equal to hc by lambda, that is one c getting cancelled, you get mc is equal to h by lambda. C is velocity of light, we are replacing with the velocity of particles, mv is equal to h by lambda, or mv means momentum p is equal to h by lambda. This is de Broglie relation, explaining wave particle duality of matter, which is very important for microscopic objects. This is corpuscular particle nature, A is equal to mc square. This is quantum theory, E is equal to h nu. Suppose we are equating the two, mc square is equal to h nu, mc square is equal to hc by lambda, cc getting cancelled, mc is equal to h by lambda, and c replaced with the velocity of microscopic particles, mv equal to h by lambda. mv means momentum is equal to h by lambda. This is de Broglie relation. This is explaining particle character, this is explaining wave character. He suggests the particle character and wave character are inversely related. For a particle of significant mass, the wave character is insignificant. For a particle of minute mass like electron's mass is negligible mass, 9.1 into 10 power minus 31 kilogram, negligible mass. The wave character is highly significant. So for microscopic objects like electron, proton, atom, subatomic particles, etc., the wave character is significant. For a moving cricket ball, particle character is significant. This is wave particle duality, de Broglie relation. This is momentum, this is Planck's constant, and this is lambda. Don't call it as simply wavelength. Call it as de Broglie wavelength. This is de Broglie wavelength. Okay. Next is uncertainty principle. Uncertainty principle. Heisenberg uncertainty principle. Heisenberg uncertainty principle. Very, very important, leading to quantum mechanical aspects of a modern atom model. Probably quantum mechanics is highly contributed by two personalities. One is Erwin Schrödinger, father of quantum mechanical aspects. And then one of the most famous personality, Werner Heisenberg. Heisenberg's uncertainty principle. He suggests that it is not possible to determine simultaneously and precisely the exact position and velocity of a moving subatomic particle like electron. Always there exists an uncertainty. Mathematically, he suggests that uncertainty in position into uncertainty in momentum is greater than or equal to h by 4 pi. This is his mathematical justification. He says always there is an uncertainty in the measurement of position and momentum of a moving subatomic particle like electron. Remember, uncertainty principle has nothing to do with a moving cricket ball. Uncertainty principle is not significant for even milligram sized or more particles. It is significant for microscopic objects like electrons. He suggests that it is not possible to determine simultaneously and precisely the exact position and velocity of a moving subatomic particle like electron. There exists always an uncertainty. This is uncertainty in position and this is uncertainty in momentum. If this uncertainty decreases, this uncertainty will increase. If you try to fix the position, velocity will change. If you try to fix the velocity, position will change. Both you can't reduce simultaneously. Mathematically, it is very much true. A into B equal to a constant. That means when A decreases, B increases. When B decreases, A increases. Simultaneously, you can't decrease both. This is uncertainty principle, which was an important idea and a very hit back basically towards Bohr model. Bohr model was not been able to counter Heisenberg's explanation. Heisenberg's argument was actually a very big blow to Bohr model. Bohr model was unable to explain uncertainty context, uncertainty principle. And then actually we are moving on to quantum mechanical model of atom. Quantum mechanical model of atom, basically quantum mechanics is related to the strong mathematical ground. It's a mathematical concept. Quantum mechanics is a theoretical idea based on the strong foundation of mathematics. Explained by various people, as I said, it is mainly done by the quantum mechanical wave equation explained by Erwin Schrödinger. This is called a quantum mechanical equation. H cap psi is equal to E psi. This is called the Schrödinger wave equation. He said every atom, molecule, system, ions, we can have a Schrödinger equation. We can have a wave equation. This is a wave equation. H cap psi is equal to E psi. H cap is a mathematical operator called the Hamiltonian operator. Psi means wave function. It is amplitude wave function. Amplitude wave function. E means energy. So H cap psi is equal to E psi. This is the simplest form of wave equation, Schrödinger wave equation. Or it may be represented like this. delta square psi plus delta square psi plus 8 pi square m by h square is equal to 0. This is another format representing Schrodinger equation. Both are same, different form of representing. This is called a Laplacian operator. This is called a Hamiltonian operator. Hamiltonian operator. And this is called a Laplacian operator. Laplacian operator. It is read as delta square. Probably the expanded version of Schrodinger equation comes like this. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square. Here one term is missing. Into E minus V into psi equal to 0. Into E minus V into psi equal to 0. This is the complete form of wave equation. I missed one small portion over here. Del square psi plus 8 pi square m by h square into E minus V into psi equal to 0. Now you see the expanded version of the Schrodinger wave equation. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V into psi equal to 0. E, you know, total energy. V means potential energy. This is amplitude wave function. In quantum mechanics, the electron system is considered as a wave. And this is amplitude wave function. Second derivative. Dou square psi means dou x square. This is the second degree derivative of psi with respect to x. This is second degree derivative of psi with respect to x. Second degree derivative of psi with respect to y. Second degree derivative of what is first degree? Dou psi by dou x. This is first degree and this is second degree. dy by dx, first degree. d by dx of dy by dx, that is second degree. d square y by dx square. Right? This is like a quadratic equation. And every atom, molecule, etc., it can have a Schrodinger wave equation. This is like a quadratic equation and can be solved. Not very simple. Requires complex mathematical calculation. But it can be solved. And the permissible solutions of this Schrodinger wave equation refer to a region outside the nucleus of an atom where the electrons can be found. That region is called orbital. The term orbital was coined on that ground. The term orbital was coined on that ground. What is an orbital? A region outside the nucleus where there is maximum probability to find an electron. How do you get that region? By solving Schrodinger equation. This is like a quadratic equation. I am just telling the peripheral idea of quantum mechanics. We can't go deep into the context. This is like a quadratic equation which can be solved for getting various solutions. The permissible solutions of Schrodinger equation refer to a region outside the nucleus where there is probability to find an electron and is called the orbital. Orbital is designated by psi. Orbital is designated by psi. And is called the amplitude wave function. And a more physical meaning is psi square. That is probability density. That is probability density, psi square. This got a greater meaning, psi square. And the characteristics of psi are explained by a set of numbers, call it as quantum numbers. Characteristics of psi are explained by a set of numbers called quantum numbers. Hope you remember quantum numbers. What are quantum numbers? Number one, principal quantum number. Principal quantum number designated by n. And the values are independent. 1, 2, 3, 4, etc. Principal quantum number, talking about energy of the orbital, talking about size of the orbital. Principal quantum number, its values are independent, 1, 2, 3, 4, etc. While the second one, azimuthal quantum number, azimuthal quantum number represented by L. Its value depends on this. L value depends on N value. It is 0 to N minus 1. L value is 0 to N minus 1. Suppose you have N equal to 1, L equal to 0, that is called S subshell. Suppose you have N equal to 2, L equal to 0 and L equal to 1. This is S subshell and this is P subshell. Suppose N equal to 3, L equal to 0, that is S subshell, L equal to 1, that is P subshell, L equal to 2, that is D subshell. So in the first energy level, we have only S orbital. Second energy level, you have S and P. Third energy level, you have S, P, D. Fourth energy level, you have S, P, D, F. Suppose you take N equal to 4, you have L equal to 0, S. You have L equal to 1, P. You have L equal to 2, D. And you have L equal to 3, F. So on. Purely mathematics. And azimuthal quantum number is talking about subshells. Their shapes of the orbitals, sub-energy level, shapes of the orbital, and their angular quantum number, angular momentum values, orbital angular momentum, explained by azimuthal quantum number. It is called a subsidiary quantum number, angular momentum quantum number, designated by L value. And the third quantum number designating orbital is magnetic quantum number, third one. Magnetic quantum number represented as M or sometimes represented as ML, because this value depends on this value. This is talking about orientation of orbitals, talking about orientation of the orbitals. You see, suppose L equal to 0, M equal to 0. The ML value, M value comes out to be minus L to 0 to plus L. This is the nature of M value. Minus L to 0 to plus L. Suppose L is equal to 0, that is S subshell. You have only one M value, 0. Suppose you are talking about L equal to 1, P subshell. You have M equal to minus 1, 0, plus 1. There are three values. I am sure all of you know. It is Px, Py, Pz. There are three orbitals. For S, you have only one orbital. For P, you have three orbitals because you have three values. How three values? L equal to 1. What are the values? Minus L to 0 to plus L. Minus 1, 0, plus 1. What about if L equal to 2? What about if L equal to 2? That is D subshell. You have M equal to minus 2, minus 1, 0, plus 1, plus 2. There are 5 orbitals. 5 orbitals. Hope all of you remember. DXY, DXZ, DYZ, DX square minus Y square, and DZ square. 5 orbitals. Right? How their orientations are coming? How their orientations are coming? Very, very important. How their orientations are coming? This is PX. PX. X-axis. This is PX. XY axis. PX. The lobes are through the axis. What is PY? This is PY orbital. What is PZ? PZ. X-axis, Y-axis, Z-axis. The lobes are coming through the Z-axis. You see, this is PX, this is PY, this is PZ. It is talking about orientation. Orientation means spatial orientation. Right? The fine spectral splitting is given by this orientation. And fine spectra was unable to be explained by Bohr model of atom. In the presence of Stark effect, have you heard about Stark effect? Zeeman effect. splitting of spectral lines in magnetic field, Zeeman effect, splitting of spectral lines in electric field, Stark effect, explained by these fine splitting. P orbital is unique, and in the presence of magnetic field, they show the orientation. Their degeneracy is lost, and they show the orientation Px, Py, Pz, like that. Similarly, dxy, dyz, dxz, dx square minus y square, dz square. Right? What is dxy? X-axis, y-axis. They are butterfly shaped, 4 lobes. This is dxy. dxy. What is dyz? yz. This is dyz. dyz. What is dxz? X-axis, z-axis. This is dxz. dxz. And dx square minus y square, there is slightly difference. Dx square minus y square, the lobes are through the axis. dxy, dyz, dxz, the lobes are bisecting the axis. Dx square minus y square, the lobes are through the axis. Similarly, dz square, two lobes and a ring, that is entirely different. dz square, two lobes and a ring. So you have to go through all these surface, boundary surface diagrams. They are called boundary surface diagrams, orbital diagrams. You must go through. Parallelly, keep an eye on a topic, node. What about node, right? What is node? What is node? Node is a zero probability region to find electron. A region where there is zero probability to find the electron. That is node. How to find the node? There are 2 types of nodes. Radial node, that is spherical node. N minus L minus 1. That is a formula for finding spherical node. Then, second one, angular node. That is L value. So radial node is equal to N minus L minus 1. Angular node is equal to L value. You can find the nodes for different orbitals. For example, if you are dealing with the 4p, what is the radial nodes? It is N equal to 4, 4 minus L equal to p orbital, L equal to 1, 4 minus 1 minus 1. You get 2 radial node. What about angular node? L equal to 1. That is 1 angular node and 2 radial node for 4p orbital. Like that. So, principal quantum number talking about energy of the orbital. Azimuthal quantum number talking about subenergy of the orbital. Magnetic quantum number talking about orientation. And there is last one, spin quantum number, not talking about orbitals and not related to Schrodinger equation. The other 3 are related, derived from Schrodinger equation. Spin quantum number is not related to Schrodinger equation. It is talking about the spinning of electrons. Right? Spin quantum number, the 4th quantum number, spin quantum number, represented as ms or simply s. There are only 2 values, plus half and minus half, indicating positive spinning and negative spinning during the pairing of electrons. When electrons are paired, it comes like this. Always pair are like this, right? It's like this. Positive half and negative half. That is spin quantum number. So quantum numbers, very important, right? And the last topic in the chapter is concerned to electronic configuration. Electronic configuration. The last topic in the chapter coming is that one, electronic configuration. These are the area we were going through so far. These are the orbital boundary surface diagrams I was explaining. And finally, electronic configuration. Electronic configuration is based on 3 principles. Electronic configuration is based on 3 principles. Number 1, Aufbau principle. Number 2, Hund's rule. Hund's rule of maximum multiplicity. Number 3, Pauli's exclusion principle. Pauli's exclusion principle. Hope all of you remember the three principles. Aufbau principle number 1, which states that the electrons are filled in various orbitals in their increasing order of energy. Electrons are filled in the increasing order of energy. That is called the Aufbau principle. How to get the increasing order of energy of orbitals? Hope you remember such a diagram. Hope you remember such a diagram. This diagram will help you to understand the increasing order of energy. This diagram, we can easily identify the increasing order of energy. You see the increasing order of energy? 1s minimum energy, 2s, 2p, 3s. You can follow this line and follow that order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. That is the increasing order of energy of atomic orbitals in which you can fill the electrons. You can fill the electrons, right? So suppose we are doing the electronic configuration, say for example, nitrogen having say atomic number 8. Sorry, nitrogen having atomic number 7. Suppose we do the electronic configuration, the configuration will be 1s, first 1s, 2 electrons in 1s, as 1s, s orbital contain only 1 orbital, 2 electrons. Then it is 2s, 1s, 2s and 2p, 1s2, 2s2, 2p3. The 7 electrons in nitrogen atom can be configured like this: 1s2, 2s2, 2p3, like that, right? It is configuration done on the increasing order of energy, or we can say it is based on n plus L value. Electronic configuration done in the increasing order of n plus L value. Suppose 2 orbital having same n plus L value, the one with the lower n value will be filled first, right? Aufbau principle. Electrons are configured in various atoms, various systems in such a way that the electrons are filled in the increasing order of energy. What is the increasing order of energy? This is the increasing order of energy. Minimum energy 1s, then 2s, 2p, 3s, 3p, 4s, so on. That is Aufbau principle. What is Hund's rule of maximum multiplicity? Which states that during the filling of electrons in p orbital, d orbital, f orbital, etc., the electrons are filled in such a way that all the orbitals are singly occupied before the pairing of any orbital is done. For example, the same nitrogen if you take, the configuration to be done in such a way, 1s2, no problem, only 2 electron filled in the s orbital. 2s2, no issue, it is filled like that. What about 2p? What about 2p? The 3 electron, are we going to give like this? No. No. The electrons are filled in such a way that all orbitals are singly occupied with a parallel spinning of electron. All electrons are made singly occupied with a parallel spinning electron. What is parallel spinning? Either all electrons are upward or all electrons downward, no issue. It should not be given like one up, one down. That is not possible. Hope you understand. That is Hund's rule of maximum multiplicity. And the third one, Pauli's exclusion principle, which states that no 2 electrons in an atom can have same set of quantum numbers. In an atom, 2 electrons cannot have same set of quantum numbers. Any of the quantum number, principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, any of the orbit, any of the quantum number value will change for 2 electrons in a system. In a system, you can't have 2 electrons with all set of quantum numbers coming same. That is Pauli's exclusion principle. Based on these 3 principles, you have to practice doing the electronic configuration. Meanwhile, There are so many exceptional cases also. If you go to chromium electronic configuration, hope you remember, it is exceptionally different. We are giving priority to half-filled electronic systems. We are giving priority to completely filled electronic systems. Half-filled and completely filled electronic systems are pretty more stable. So there will be some exceptional configurations, particularly when it comes to D and F block elements. Hope you know. In copper, there is an exemption. In chromium, there is an exemption. In chromium, we are expecting a configuration at the end portion of the chromium atomic number 24. At the end portion, we are expecting a configuration 3D4 4S2 according to the rules and regulations. But what is actual configuration known to all of you? I think it comes as 3D5 4S1 because 3D5 is exceptionally stable. Because it comes as 1, 2, 3, 4, 5. The singly occupied electron system is more stable. There are many theories explaining its reason of stability. Symmetric electron systems are more stable. One theory. Exchange energy is maximum. Maximum number of exchanges possible. That is another theory. What is meant by exchange? Suppose you label this as one electron. It can exchange with this, it can exchange with this, it can exchange with this, it can exchange with this. It's able to make 4 exchanges. So half-filled and completely filled systems are more stable due to exchange energy. Right? Or there is another theory, symmetric configurations are stable. Like that. So exceptional configuration, particularly mainly noticed by D and F block elements, you need to go through. Right? These are the main coverage topic from the chapter structure of atom, not states of matter, structure of atom, right? Let me make a brief conclusion before stopping the class. We started from subatomic particle, right? Cathode ray experiment, various atom model, properties of various subatomic particles, right? Then electromagnetic spectrum, absorption spectrum, emission spectrum, various properties of wave characteristics, quantum theory, black body radiation, hot body radiation, very important topic, photoelectric effect, atomic spectra, spectral series for hydrogen atom, Lyman series, Balmer series, Paschen series, bracket series, etc. Various Bohr model equations, energy of nth orbit, radius of nth orbit, velocity of nth orbit, angular momentum equation, mvr is equal to nh by 2 by angular momentum equation. Then coming to quantum mechanical idea, de Broglie relation, dual nature of matter, uncertainty principle. Then quantum mechanical equation, Schrodinger equation, quantum numbers, principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. And finally, the rules and regulations and practices to be done in electronic configuration of Bohr principle, N plus L rule. Hund's rule of maximum multiplicity and Pauli's exclusion principle and various exceptional scenarios, etc. And we need to apply all these contexts in variety of problems, that is theoretical as well as numerical problems across the competitive questions which we are going to do in the classes. Okay, so that comes the end of the rapid revision class on chapter 2, structure of atom. Bye, see you.